Hello everyone, welcome back to ChemOrgChem. In today's episode, we are continuing to explore the sodium cyanoborohydride, a mild reducing agent with a wide range of applications in organic synthesis. So this is the second episode in our series of sodium cyanoborohydride. So if you have not watched the first episode yet, be sure to check it our channel page. Now let's start by brief recapping what we covered in the first episode. In first episode, we have seen the preparation and structure of sodium cyanoborohydride, and also we seen that chemoselective reducing properties of sodium cyanoborohydride, which is mainly depends on the nature of medium as well as the pH of reaction medium. So in that case, we already seen that hollow or tosylate displacement, reductive displacement reaction. And also in our first episode, we already see that in acidic medium, the selective reduction of carbonyl as well as imine and ammonium salt. So in this episode, we are going to see the reduction of enamines, oxime or oxime derivatives, tosyl hydrozones and epoxide by using sodium cyanoborohydride. So let's start with our first enamine reduction by sodium cyanoborohydride. So you just remember that all these reactions should contact under acidic medium. So first you consider this example. So we already know that enamine in the presence of acid that quickly convert into the corresponding imine form. So this enamine tautomerism is present at equilibrium. So therefore, when you apply sodium cyanoborohydride, when enamine it convert into the imine form, that quickly reduce into the corresponding amine compound. So let's see some examples. Here you see this enamine is prepared from cyclohexanone with pyrrolidine. So when you treat with sodium cyanoborohydride, that will quickly convert it into the corresponding aminated product. So let's moving on oximes. So just like imines, oximes can be reducible by using sodium cyanoborohydride. Now you consider this example. When you take the cyclopentanone and react with hydroxylamine, you will get corresponding oxime compound. That oxime compound quickly reduced by sodium cyanoborohydride, which provide corresponding aminated product, hydroxyaminated product. So next we moving on a reductive deoxygenation of aldehydes and ketones. So in another way, we can say this reaction is a reductive alkylation. According to this reaction, now you consider either ketone or aldehyde which initially react with tosyl hydrazine. After the reaction, you will get the corresponding tosyl hydrozones. In these tosyl hydrozones, in the presence of acid, that readily protonate this nitrogen. So resulting that you will get protonated form. So after that, sodium cyanoborohydride that quickly reduce this center, resulting that you will get this intermediate. Now base quickly remove this hydrogen. Here base means mostly in this case acetic acid is useful. Therefore, when you use acetic acid, definitely in the medium you will have acetate ions. That acetate ions quickly takes the proton from here, so that resulting that this electron shifted here, then followed by kick off this tosyl unit, you will get corresponding this intermediate. So after that, so these electrons are shifted here, this H plus ion shifted towards to this carbon center, resulting that you will get the corresponding hydrocarbon along with nitrogen gas. Next, we moving on. Reductive deoxygenation of alpha beta unsaturated ketone. So this mechanism is slightly different compared to our previous case. Now you consider this example. When you use sodium cyanoborohydride, we would expect to get this product. However, this product is not observed. Instead of that, we get this kind of product. So now you closely look this product, what happened? Exactly. So initially that this bond is reduced, then followed by double bond isomerization takes place to provide this absorbed product. Let's see magnetically how this reaction is occurred. So initially, when you use sodium cyanoborohydride in the presence of acidic medium, that will readily reduce this center, resulting that you will get this intermediate. So after that, that tosyl part as well as this hydrogen unit going away, resulting that you will get this intermediate. So we can draw this intermediate like this. So after that, here you see this hydride ion transfer into the center, then followed by this electron shifted towards here, then followed by breaking off this carbon-nitrogen bond, which leads to generate nitrogen gas along with our product. So let's see some of the examples for our reductive deoxygenation or reductive alkylation protocol. So now you consider this ketone. In the first step, when you use tosyl hydrazine in ethanol, that will give corresponding tosyl hydrazone, then followed by use of sodium cyanoborohydride, which quickly reduce into the corresponding hydrocarbon unit. So this is the another example, but this one is contain alpha beta unsaturated system. So therefore, when you use sodium cyanoborohydride, that reduction as well as isomerization takes place to provide this corresponding product. Next, we moving on epoxide. Epoxides also reducible by using sodium cyanoborohydride in the presence of suitable Lewis acid. Now you consider this example. When you use Lewis acid that readily coordinate with the epoxy oxygen, resulting that you will get this type of intermediate. So now that hydride ion can attack this center as well as this center. However, that ring opening of epoxide is dictated by the formation of more stable carbocation intermediate. So now you consider, because of that coordination, you will get the delta positive character in this carbon that can stabilize by methyl as well as CH2 group. However, at the same time, when you put the delta positive in this carbon center, that can stabilize by only the CH2 group. Therefore, this carbocation center is more stable compared to this. Therefore, when you use sodium cyanoborohydride, here you see that hydride ion attacks this center, resulting that you will get this type of product. And another important point is this hydride attack always takes place by the backside of that epoxy Lewis acid complex, resulting that you will get this type of alcohol product. So now you see this hydrogen attacks takes place from pack side, resulting that you are getting this type of stereochemistry. So now we move on another example. Now you see this epoxide. So here zinc triflate acts as a Lewis acid. Therefore, when you use zinc triflate, that will generate delta positive, that means carbocation. This center, so this center is more stabilized because of this aromatic group. Therefore, that when you use sodium cyanoborohydride, that hydride ion attacks this center, resulting that you will get this type of corresponding alcohol product. So here are some of the practice problems. When you get the free time, you just try to work it out, and there you have it. So if you find this video helpful, don't forget to subscribe to our channel for more content like this. And finally, thanks for watching and see you next time.